The section 6.7 is about adsorption. Does anybody want to tell me why is adsorption and absorption, the differences? Adsorption and absorption, what's the differences? 0.5? No? Yes, please. B 的 B 是吸收还是吸附？吸收，对不对？那 AD 是什么呢？吸附。Okay, very good. So the absorption is regarding about the things which is absorbed in the materials. The absorption, AD, is something to do with the things attached on the surface. So that's the difference between adsorption and absorption. But in section 6.7, it's about adsorption and desorption. Right, so basically is that basically the adsorption is the gas or liquid absorbed on the surface of the solid. That's what we call adsorption now. And when the things release on the surface, that's what we call desorption. Desorption. Okay, desorption. Right, so adsorption and desorption, which attacks on the surface or move away from the surface. Right, and then the second thing we learn is adsorbent and adsorbate. Adsorbent is the things that this is solid surface, right? So this is what we call adsorbent. Adsorbent. The adsorbate is the things on the surface as a liquid or as a gas. Okay, so this is the. So you need to know what is adsorbent, what is adsorbate. Okay, and also we also know that adsorption is kind of exothermic process. Exothermic process. Okay, so exothermic process is it releases the heat and make the system become very stable. And adsorption is endothermic. Endothermic is that you absorb the heat. Okay, so adsorption releases the heat. Desorption is absorb the heat. Okay, receive the heat, the energy. And also we know that adsorption is the capability, which is a function of species, pressure, and temperature. Okay? So the adsorption capability is a function of species, which is you have different adsorbent and you have different adsorption capability. For example, we talk about the adsorbent. One of the cases of the adsorbent is activated carbon, right? Activated carbon. The activated carbon, which is a good adsorbent, and you can absorb many species. And this is another type of absorbent which we call zeolite. Zeolite is another absorbent, especially for gas. Especially, for example, if you want to do the separation of the nitrogen or oxygen, and zeolite will be one of the very good candidate to have absorption for the separation of the gas, for the separation of the nitrogen and oxygen. Okay, so absorption capacity is function of species and also the function of the pressure. The pressure is, if we increase the pressure, the absorption capability will be increased. Okay, for example, here you have the high pressure means what? You have more species. More species. If you have more species, that means the absorption capacity will be increased. Okay. However, in regarding of the temperature, if we increase the temperature, the absorption capability will be decreased. Why? Because if we increase the temperature, the adsorbate will be unstable. Why? Because adsorbate tend to become liquid or gas, not intend to become solid if we increase the temperature. Okay, so this is absorption capability. And finally, what we learned in section 6.7 is absorption isotherms. Absorption isotherm, which is X over start, this is the amount of absorption. versus the concentration or pressure. And this is one of the cases we learned from the last lecture, which is on Monday. So if we, for example, here, if we increase the pressure, increase from 10, 20, 40 to 140, and this is the amount of the species absorbed on the surface. And as you can see, if we increase the pressure, this black dots means what? Means the increase of the amount of the species on the surface. So as you can see, this increase, this will be increased. Eventually, this will reach to a maximum amount. This will reach to a maximum amount. Right. So, and there's one important or famous topic is what we learn is Langmuir isotherms. This is the equation of Langmuir isotherms. Langmuir isotherm is X star is a proportion of the PI. PI is the partial pressure of the adsorbate, and CI is the concentration of the adsorbate. So if we want to simulate this black dot, this curve is what we call Langmuir isotherm, because this is the kind of empirical equations. So you do an experiment, and you find out the curve represent this data. So this is the Langmuir isotherms. Okay, this is what we learned in section 6.7, absorption. And finally, there are some applications for the absorption. This is one of famous applications, air separation by pressure swing absorption. As you remember that if we increase the pressure, the absorption capacity will be increased. So we increase the pressure and decrease the pressure. Increased pressure is absorption. Decrease the pressure is desorption. So you have two tanks. One tank is increase the pressure. So as you can see, if we have a good absorbent in this tank, and if we increase the pressure, as you can see here, the nitrogen will be released. The small oxygen will be trapped in the absorbent. Okay, so you got high purity of nitrogen release here. And then this is increase the pressure, right? This is A bar, and this is 1 bar. You decrease the pressure. You decrease the pressure. When you decrease the pressure, the absorption capacity decreased. So the oxygen will be released, right? Because oxygen was absorbed on the surface of the absorbent, and then released here. So you will have a high purity of nitrogen in this stream and high purity of oxygen in this stream. Okay, so this is air separation. So you can get more pure oxygen, or you can get more pure nitrogen. Right, so this is already commercialized. You can have a industrial scale, or you can have a family scale. For example, this is you can have this kind of machine at home or in hospital. So we can produce this is called oxygen generator, oxygen concentrator. It cannot reach the 100%, probably 85%, 90%. It depends on the process. So you can use this machine in the hospital or at home for the patients. Okay, so this is example like this. So this is what we learned in section 6.7 regarding about the absorption. And today we are going to talk about energy and energy balances. Right. So from chapter 4, chapter 5, and chapter 6 is regarding the energy mass balance. But for the energy balance, we are going to talk in section 6, chapter 7, and chapter 8, and chapter 9. Unfortunately, we only have limited time to talk about energy, but all the concepts of the energy balance and mass balance are the same. They are all input equal to output. So it can be mass input equal to the mass output, energy input equal to the energy output. So this is important, and you already learned this from in chapter 4, chapter 5, and chapter 6. So, and we still have a little bit time for 2 weeks. So, for 1 week, right? Today and Wednesday. So energy. So we start to talk about energy. Okay. First of all, energy is expensive. The country who own the energy they will become very rich country, right? Like United States, they have energy, right? China, they have energy, okay? And Mid East, they have energy, so they become rich. So energy is expensive, and then energy can be provided by what? Energy can be provided by many resources. For example, free energy you can get from the sun. You can get it from the winds. You can get it from the tires. Okay? And then, if you want to keep the energy, this is called hydroelectrical power. The waterfall and the dams. This you keep the energy, potential energy, and you release and you produce energy out. Of course, and then you can use some of the fuels. Fuels can be gas. Right? Natural gas. It can be oil, crude oil. It can be solid like coals. These are the fuels for you to use. And you burn the fuels and produce the energy, produce the thermal energy. Okay, thermal energy, and if you produce the thermal energy, you can produce some of the electricity. Okay, and then last one will be nuclear power. Nuclear power, you all know this. So this is the resources or energy can be provided by these different ways. Okay, so now let's start to know that what is energy balances. So you don't want to waste energy, right? So waste energy leads to reduce the profits. So you waste energy, you lose money. So you want to keep energy. You want to use energy efficiently. So as an engineer, design a process, one of your principal jobs would be to account carefully for the energy that flows in and out of each process unit, and to determine the overall energy requirements for the process. So again, the flow in, the energy input of the energy and output of energy. So it's flow in and flow out of each process. So for the energy balances, for example, if I ask you how many powers is required to pump 1,250 cubic meter per hour of water from a storage vessel to a process unit. So you need to calculate if you want to pump this amount of water to a tower. So you need to have energy to pump this water to another place. So how many powers? What does that mean, power? Power is energy per time. So if anything related to this second or this hour or this year of the energy, that means this what we call is power. Power. Okay? It's energy per time is called power. And then another question might be how much energy is required to convert 2,000 kilograms of the water at 30 Celsius to a stream at 1,800 Celsius. So this amount of water, you need to heat up this amount of water from 30, okay, to make it become steam, 180 Celsius. This steam can be heated up and energy is required. Okay? So what is this for? This is for turbine, right? It can become turbine because this is vapor. Okay? Right. And then at higher exothermic chemical reaction A to B. For this is chemical reaction, it releases the energy out. Taking place in the continuous reactors, if a 75% conversion of A is to be achieved, So at what rate must energy be transferred from the reactor to keep a constant, the content at a constant temperature? So this is another question, say that if this conversion rate is 75%, okay, from A to B, and then how can you control the temperature? Is another question. Finally, how much coal, you need to have, you burn this coal and make it have a thermal energy, right? How much coal must be burned each day to produce enough energy to generate the steams to run the turbines to produce enough electricity to meet the daily power requirements of the city of the 500,000 people. So this city has 500,000 people, and you need to provide sufficient energies or electricity to this city, and how much coal you need to burn per day in order to reach the requirement for the electricity used in this city. Okay, so these are all the questions regarding the energy, and you need to produce the energy. You need to do the calculation. And you don't want to waste the energy, so you need to know what's the energy balance in this process. Right. So that's why we need to know, or we need to learn this. Okay, so the section 7.1 is the form of the energy, and we want to learn the first law of the thermodynamics. First law of the thermodynamics. When you go to the third grade, third year in this in the chemical engineering department, you will learn thermodynamics. You will start to learn the first law of the thermodynamics, second law of the thermodynamics, third law of the thermodynamics. In this first year, we don't talk about this in detail. I just tell you roughly what's the first law, second law, and third law of the thermodynamics. But before we talk about this, we need to know what is the thermodynamic system. This is a system. The system is the material and the radiative contents of a microscope value in space that can be adequately described by the thermodynamics state variables such as temperature, entropy, internal energy, and the pressure. So this is a system. For example, you have a hypothetic box. In this box, this is what we call system. And inside the system, the variables can be temperature, entropy, internal energy, and pressure. You might wonder, Professor, what is internal energy? We are going to talk about this in detail, okay? So the thermodynamic system is always enclosed by walls. This is called walls, okay? And walls can be regarded as boundaries. So the outside of this boundary is not inside, is not a system, okay? That separate it from its surroundings. So this surroundings is environment. So this system, the outside of this system is surroundings. So this is system, boundary, and surroundings, or this constrained system. So you have to always keep this in your mind. Thermodynamic system is related to system, boundary, and surroundings. Okay, this one of the most simple case is this. You have a piston here, and this is, you have piston here, and this is a container piston, and then this is what we call boundary, and then outside surroundings. So piston can move, right? Piston can move up and down, but this is wall. So what is boundaries? Boundaries is a wall restrict passage across it by some form of the matter or energy. So this is, you can block energy or materials or matters, weight. Okay, make it connect indirect. So this is an isolation for the outside and inside. Okay, sometimes the world is no more than an imaginary two-dimensional closed surface through which the connection to the surroundings is direct. So this is kind of imaginary. You can use your imagination to think of this system. Okay? And surroundings is the reminders of this universe that lies outside the boundaries of the system. It is also known as the environment. And the reservoirs is this, right? Depending on the type of the system, it may interact with the system by exchanging, right? You can change what? Change inside, the things inside and outside, like what? Like material, like mass, energy. Okay? So when you change this, including, you can increase the temperature, which we know the energy, the thermal energy, which is heat, and work. Okay? And also work. So not only the mass energy, but also momentum, electric charge, or other conserved properties. But here we only talk about mass energy and momentum for chemical engineers. Right. So now let's go to the total energy of the system. I'm sure you learned this when you are in high school, but let's recap what you have learned in your high school. The first one is kinetic energy. What is kinetic energy? So the translation of energy, kinetic energy, is energy due to the translation motion of the systems as a whole relative to the sound frames of the references, usually the Earth's surface. Okay, so you have some standard point and you move it, and this is the things. So the kinetic energy is not only translation, kinetic energy from A place to B place, but also rotation kinetic energy. So for example, this ball can rotate, right? So rotate require energy. So this is what we call rotation kinetic energy. So energy due to the rotation of the system about some axis. So you have axis here, and you can do rotation like this. So this requires energy. In this case, we only deal with the translation kinetic energy in this text. So this topic or this lecture or this course only talk about translation kinetic energy. Okay, not rotation kinetic energy. How about potential energy? Potential energy is energy due to the positions of the system in the potential field. Normally, when we talk about potential field, it's a gravitational field. Okay, it's not electromagnetic field in our course. Okay, so we will deal only with the gravitational potential energies in this text. So not electromagnetic fields. So for kinetic energy, we only talk about translation kinetic energy. For the potential energy, we only talk about the gravitational potential energy. Okay? So the total energy involves kinetic energy, potential energy, and also internal energy. So what is internal energy? So all the energies passes by a system other than kinetic and potential energies. So if we have total energy, and total energy equal to minus kinetic energy, minus potential energy will be equal to internal energy. So other forms, other from the translation, rotation, gravitational, electrical fields, other forms are all internal energies. Okay? Right. So there are many types of internal energies. Let's talk about this. So when you throw a ball from the ground and throw a ball to the sky, for example, the potential energy, the kinetic energy will decrease, right? The potential energy will increase. You know that already. And after that, it dropped by gravity, right? So the kinetic energy reaches to zero and start to increase, and potential energy decrease. So you have a kind of transformation of the potential energy and the kinetic energy. However, what is internal energy? So energy is, the definition of the internal energy is the energy due to the motion of the molecules. One of the internal energy is energy due to the motion of the molecules related to the center of the mass of the system. So when this ball moves from here to here to here, you have many molecules in this ball, in this baseball. Okay? Okay, and then the motion of a molecule inside moving, you don't know. It's moving, right? Because the temperature is not 0 Kelvin. So the molecule inside is moving. This is called what I call internal energy. Okay, and internal energy, and energy due to the rotational and the vibrational motion of the electromagnetic interactions of the molecules. So not only these molecules will move around, maybe, but also what? This molecule will rotate. For example, this is one of molecules. Rotate or vibrate inside these balls. These are also called internal energy. However, you don't care about this. You just regard this baseball as a whole, right? As one, and you saw it from here to here, and just the transformation of kinetic energy to the potential energy. And this internal energy, you don't care at this moment, right? And not only this, but also the energy due to the motion and interactions of the atomic and the subatomic constituent of the molecules. So when you take one molecule or take one atom out, inside there's a proton, neutron, and electrons. There's kind of interactions, right? So these are also regarded as internal energy. So from the object, inside the object you have molecules. Molecule will run and move. Molecule itself will vibrate, rotate, and if you take a single atom, you will see the proton, neutron, and the electrons. They are moving. Okay, these are all regarded as internal energy. Right. So now we already know kinetic energy, potential energy, and internal energy. There are another two terms we want to know. The one is called heat, another one is called work. So what is heat? The heat is, let's think of this. Suppose a process system is closed. This is closed, right? So no mass transfer across its boundaries while the process is taking place. So this is one of the case we can think. So this is the mass inside and the piston here and surroundings. So no mass move away from this system. So this is supposedly system, right? Energy might be transferred between such a systems and the surrounding into two ways. So if you have system here, the mass cannot be moved away, but energy can be transferred. In what way? One is heat. So that if you push this piston down, and the system might get hot. The temperature increase. If the temperature increase and you have a high temperature and low temperature, the heat will transfer from inside to the outside. So this is the first way is as a heat. The energy that flows as a result of the temperature differences between the system and its surroundings. So system and surroundings, the heat will transfer. Okay, the direction of the flow is always from the higher temperature to the low one. So temperature high go to temperature low. The second way is work. So when you push this down and you move it, the piston might be goes up, right? So as a work, the energy that flows in response to the energy driving force are temperature differences, such as a force, torque, or voltage. So it's not only by mechanical force, it can be electrical voltage. Okay, so this is kind of work. So for example, this is the example, right? If a gas in a cylinder expand and move a piston against the restraining force. A gas does work on the piston. The gas work on the piston, right? So the energy is transferred as a work from the gas to its surroundings, which including the piston. So piston will be pushed up, so you make a work. So this is another example. So heat and work are two different ways to transferring energy from the system to another. Okay? So now we learn 5 terms: kinetic energy, potential energy, internal energy, heat, and work. So this is thermodynamics. So units of the work. What's the unit of work? The work is a kind of energy. The unit is the same as energy. Okay? So what's the energy? Unit of the energy. You know, energy in very simple ways, according to Newton's motion law, energy equal to what? Force times distance. So it can be force times distance. So this joule so this is called joule. Joule will be SI system. The dyne times second centimeter will be ERGS, right? This is CGS system. And this is pound feet times pound force. This will be American engineering system. So unit of the work is the same as the unit of the energy. SI system, CGS system, and American engineering system. However, we have some I think you don't learn this much, but if you do the weight training, or if you go to do shopping, you find foods, you might see this, the kcal or calorie, right? Calorie or BTU. BTU is what? British thermal unit for short. BTU, British thermal unit. So this is also the unit of the energy. Okay, so amount of heat must be transferred to a specified mass of the water. So this unit is regarding with the water to rise the temperature of the water by a specified temperatures intervals at a constant pressure at 1 atm. So you keep the temperature at 1 atm, and you rise the temperature of water for 1 degree. For example, kilogram calorie, or we call kilocalorie, will be, you increase temperature from 15 to 16 Celsius, and this is called 1 kilogram calorie. Okay, and if you say the car is 1 gram, and this will be also increased to 1 from 16 Celsius to from 15 Celsius to 16 Celsius. You increase 1 Celsius. Right. So another energy unit is BTU, you know, British thermal unit. British thermal unit, we use BTU, is 1 pound, its mass of water is 1 pound. And you increase temperature from 60 Celsius, Fahrenheit to 61 Fahrenheit. Okay? So this is units of the work. So now you know the unit, you know 5 terms of the energy. And then now, what is thermodynamics? Thermodynamics is a branch of the physics concerns at the heat and the temperature and their relation to the energy and works. So there are 4 laws of the thermodynamics. The first one is called zero law. These zeros laws of the thermodynamics. What is 0 laws of thermodynamics? We already learned this. No, we haven't. If 2 systems are each of the thermal equilibrium with the third one, they are also the thermal equilibrium with each other. What does that mean? If the A is equilibrium with C and B is equilibrium with C, that means what? A is equilibrium with B. So this is the 0 laws of thermodynamics. This is very straightforward and easy to understand. Okay? So you learn this. This is a very logical way to learn. A equal to B, A equal to C and B equal to C. So A equal to B. This is the 1. It's first zeroth law of thermodynamics. What's the first law of thermodynamics? The first law of thermodynamics is the conservation of energy. Energy input need to be equal to energy output. Okay? The internal energy of the isolated system is constant. So if you have a system, the energy is conserved. Okay? So this is the first law of thermodynamics. We have more explanation for this. Okay, so another one is second law of the thermodynamics. What is second law? The second law is the heat cannot spontaneously flow from a cooler location to a hotter location. So if you have a place where it's a higher temperature and low temperature, the heat will always transfer from hot temperature to low temperature. There's no way the heat will transfer from low temperature to hot temperature, right? Otherwise, this is against the nature. This is against the nature. So heat cannot spontaneously flow from a cooler location to a hotter location, unless you do something which is you force them to do so. Otherwise, this is against the nature, right? So this is very easy to understand. So the third law of the thermodynamics is what? A system approaches to absolute zero. So the system approach absolute zero means what? The temperature reaches to 0 Kelvin. So all the processes cease, and the entropy of the system approach to the minimum value. So everything stop, right? Molecular stop. You stop. You are freezed. 0 Kelvin. So everything is 0. All the processes ceased. So this is the third law of the thermodynamics. Of course, I just told you this is a very simple explanation for the laws of thermodynamics. We have more complicated process or complicated explanation for you when you go to a higher level of in this department. Right. So before we talk about these laws in details, okay, let me finish this then. So let's talk about first law of the thermodynamics first. So what's the first law of the thermodynamics? We know this is laws of the conservation of the energy, right? So what do we learn about general balance equation when we study in the chapter 4? I hope you remember these terms. Accumulation equal to input plus generation minus output minus consumption. This is what you learn, right? And since the energy cannot be generated or cannot be consumed, so accumulation must be equal to input minus output energy. Okay, so if we want to explain this in terms of energy, that means what? The rate of the accumulation of the energy in the system equal to plus. This is plus, okay? The rate at which energy in this case is kinetic, potential, and internal, is carried into a system by input streams. So this energy input to the streams, which is plus, right? And then when you move and after that, you learn 5 terms, right? So this needs to be plus again, the rate at which it enters as a heat and work. So if we have a system, kinetic energy, potential energy, internal energy, heat and work can be entered to this system. Okay, and then you minus what? You minus the rate of at which is transported out of the system by output streams. Okay, so output can be what? Kinetic, potential, internal, heat and work. So the equation becomes accumulation equal to the input minus output. So this is explanation in terms of the thermodynamics. And this is the first law of the thermodynamics. So if you check in the wiki, in the internet, the first law of thermodynamics is internal energy of the isolated system is constant. So this is a conservation of the energy. Okay? So this is a closed system. So this is drinking bird. Do you know drinking bird? You know drinking bird? Drinking bird is that you have a tube go to here and you have a liquid. And you have two balls here. So the drinking bird is also known as insatiable birdie or dipping bird. Dipping bird is that this bird will drink water all the time. Okay, toy is heat engine. Actually, this is kind of heat engine. Okay, have you seen this before? You go to sizing areas, they all sell this on the street. Okay, maybe the motion of the bird drinking from the water source. So how does it work? Two glasses balls, one here, join a glass tube. The glass tube is here, and this tube is almost reached to the end. Okay, the tube is turned nearly all the way to the bottom balls, and then attract to the top of the balls. It does not extend into it. So this tube is only here and up to here. So this is above here. So a space inside a bird contains a fluid. This is fluid, and sometimes it's with color. Okay, the fluid is typically dichlorine methane. So this is kind of high vaporized liquid. Okay, so it has a low boiling point. It can be easily changed from a gas to a liquid. So according to the temperature differences, this liquid can be changed to the vapor rapidly. So that's why this can become a drinking bird. Okay, some liquid in the bottom and some liquid in the top. So that's why some liquid in the bottom, some liquid on the top. If this is heavier, this bird will dip the water. And if it is heavier, this will go down. So you will keep on doing this. So this is kind of heat engine. That's what we call. The transfer of the energy is heat and work. So you have heat, thermal energy, right? And this is dipping is kind of work. So heat is converted to the work is converted to the heat. So drinking bird is a great way to see the first and second laws of the thermodynamics. So they use first law and second law of thermodynamics to create this toy. Okay, it's not okay. So let's take a look how it works. Oh. Right. Okay. So now is section 7.2, kinetic and potential energy. This is very easy. You learn this when you are young. So you know, kinetic energy is, if we don't think of rotation, the kinetic energy is very simple. You learn this when you are in junior high school, I think. Okay, so if a fluid enters a system with a mass flow rate and a uniform velocity, the rate at which kinetic energy is transported into the system by a fluid. So if we have a kinetic energy which is overdot, what does that mean? It's energy divided by time, right? So how do we call this? If an energy has an overdot on the top, that means it's energy divided by time. How do we call this? 0.5 point. Energy divided by time. Yes? Power. Thank you. That's correct. Power, right? So you learn this when you are in high school or junior high. And now you need to learn this. Why? Because this is a continuous process. If it's energy divided by time, that's power. Right? So a fluid, you think of a fluid all the time, enter a system which is a mass flow rate. Okay, so how can we change to here? It's m dot, right? M over dot. M over dot is mass divided by time. That means what? Mass flow rate. Mass flow rate. Okay? So this is the kinetic energy. How about, so this is an example. Kinetic energy transport by a flowing system. So this is a pipe. So a water flow into a process unit through a 2 centimeter ID. ID means what? Internal diameter, okay? Inside diameter. Okay. Pipe at a rate of the 2 cubic meter per hour. Okay, so there's this is what? This is mass flow rate or volumetric flow rate. This is a volumetric flow rate. So we understand the water flow from here to here with a flow rate of the 2 cubic meter per hour. And we want to calculate the key, the K, over that, it should be here, okay? For resistance in the joule per second. So this is power. So you want to know if we do this, what's the energy, what's the power flow from this place to here, okay, per second. So this is a volumetric flow rate, which is V over dot equal to 2 cubic meter per hour, right? And you have out. So we understand this this kinetic energy over dot is this, and we know this is the equation. So how do you transfer volumetric flow rate to mass flow rate? Density, conversional factor, right? Density. So if you know the density, you know this. So volumetric flow rate changes to mass flow rate is density. And how about this one? This is velocity. Power 2. What is velocity? How do you use this for velocity? Velocity is what? It's meter per hour, right? Meter length per second, or length per time. So you just divide it by what? That's what we call linear velocity. So this is the volumetric velocity. Linear velocity will be what? Linear velocity will be volumetric flow rate. To change to linear velocity will be what? You have a diameter. So diameter, you divide it by diameter. This will become linear velocity. Okay? From cubic meter to become meter. What you need is the diameter of this tube. The area of this tube. You know the diameter, right? So you need to know, it's easy for you to calculate diameter. The area. You know the diameter of this tube, so you can calculate the area of this tube. So if the area of this tube here is meter power 2, so it can become meter power, a cubic meter become meter by the area of the pipe. Okay? Easy. So if we have Wednesday we don't have Kahoot. If we have a Kahoot, I might have this question for you. But Wednesday we don't have Kahoot. So that's it. Right. The next. So you learn the kinetic energy. Kinetic energy divided by time will become power. Right. How about gravitational potential energy? So gravitational potential energy, you learn this when you are in junior high. So energy will be what? mgh. M will be mass. G will be acceleration of the gravity. Z will be the height. Right? So if a fluid enters a system with the mass flow rate m over dot, and if a relation Z related to the potential energy refer planes, then this one. So this is what you need to learn as a college student. So again, the potential energy over dot, that means what? Is a power. And equal to the mass over dot times G and times height. So this is called gravitational potential energy. So we normally interested in the change of the potential energy when a body of the fluid moves from one elevation to another. So from one potential energy to another potential energy, there's the differences, right? So this is what we learn. Okay, so another example, the crude oil is pumped at a rate of 15 kilograms per second from a point 220 meters below the Earth's surface to a point of 20 meters above the ground levels. Calculate a attendant rate of the increasing of the potential energy. So this is easy. You have a water, and you want to pump the water to a higher place. So that's why you need to know the differences between the height. So this is equation you need to know, and this is Z minus 2, Z2 minus Z1. And this you got this. So this is power, the unit of the power is called watt. Joule per second is called watt. Okay? Right, I think the section, we don't have time for chapter 7.3.